Maybe it's rainy. People don't want to drive in the rain. More people usually come kind of right before because people are coming from work and stuff too. So
Did I miss the midterm?
yes, yeah. So we're having a midterm next Wednesday, 4/17. So the format of the midterm, like you've had it before, you know, like that conceptual questions and problem solving questions. And so for 4/17, there's gonna be no MATLAB on the exam.
So just getting the right.
Exactly. Yeah. So I'm going to give you a differential equation. I want you to basically give me the finite difference equations for it. You can have a cheat sheet. So 8.5 by 11 sheet of paper, both sides written or typed. I'm going to put out a study guide tomorrow to help you study. I'll be recording a review video on Monday. It's a little bit late, but I'm going out of town this weekend, so I'm not able to record it when I usually do. And then homework three is due Monday. So homework 3 is it's a little bit short, I know, but it's shorter than homework 2. So yeah.
Dr. Chan, are you able to hear me?
Yep, I can hear you, Ivan.
Okay. Thank you, sir.
Real life application.
Mm-hmm. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? I'm an audience of one today in the classroom. Okay, all right. So the plan for today, just like I promised you guys, oops, I forgot to change the date. Just like I promised you guys last week, we're going to talk about the midterm project today. I forgot to change it. This should say spring 2023, but it doesn't really change anything. I did change the due date. And so the due date is exactly a month from today. And so you guys have 4 weeks to work on it. Okay. If you want to put this in context in terms of the break schedule, this is actually going to be the Monday of spring break. Okay. So actually spring break actually comes at a nice time because, that gives me extra time to grade it. And so if you can get it, so, by setting this due date, you'll know what you have on the midterm project when you come back from spring break. Okay. And so today, the first thing I want to do is to kind of just talk about what the project is, what you're going to be expected to do, what all the deliverables are, and kind of what each aspect of the project is going to be. Okay, so we'll probably spend the first 20-30 minutes talking about that. And then we're going to move on to talk about element types after that. Okay. All right. I think that's about it. So we did activity 3 last Wednesday. So you guys know that's due this Friday. And so, we're, one thing to keep in mind is that, we're still going to be working on activities kind of in parallel with the midterm project being out there. So, make sure that, you don't wait until the last minute to do the midterm project because we're still going to be doing other activities. We're still going to be doing other stuff in the class. And so, I'm giving it to you now so that you have that kind of month-long time to work on it slowly throughout then. And, I think it's going to be about a month's worth of work kind of in parallel with everything else that we're doing in the class. Okay. All right. Any questions on anything before we get started for today? Okay. Okay. All right. So let's talk about the midterm project. So basically the midterm project for EGME 540 is to do what I consider to be a full finite element analysis and to write the corresponding technical report. Okay. And so up until this point in the class, we've done 3 activities. And so through those 3 activities, we've covered what I consider to be the basics of finite elements. Okay. And so at this point, I think everyone's pretty familiar with the process. And so, first step is you get your geometry, then you set your material properties, then you mesh, then you set boundary conditions, you run the simulation, and then you analyze the results. Okay. So that's kind of been the constant in kind of all 3 of our activities so far. And now you're going to put it in practice on a more practical part, on a much more complex part this time, but without, I'm not going to be kind of walking you through the process. Okay. Okay. And so here are your 2 subjects. Okay. And so for this project, I give you an option. So you can either work on one of these 2 geometries. Don't do both. You don't get any extra credit for doing both. And in fact, if you do both, I'm just going to grade 1. And so, unless you really want to, there's no benefit to your grade to doing both. So I want you to choose one. Okay. And so the first option here is what I call a shaft housing. And so you kind of have this kind of weird contraption here where you have a shaft and it's kind of inside these kind of 2 bearings here. Okay. And then option 2 is this kind of valve structure. Okay. So I'll call this the globe valve. Okay. And so for this project, first thing you're going to do is you're going to pick one and then you're going to do your analysis on it. Okay. One thing that you'll notice right away about these 2 geometries is that, first of all, they're a lot more complex than the geometries that we've worked with. Okay. And especially, there are a lot of extra parts here. Okay. And so one thing that you'll find often a lot in practice is that when you get your CAD models to do finite element analysis, a lot of times they contain a lot of extra parts that you don't need for the simulation. Okay. And so kind of the first consideration that you're going to have to do when you're getting these parts is to think about, what's kind of the most important parts of this structure? What are the parts that are kind of bearing the most load? And what are some parts that I can suppress? Okay. And so it's kind of very similar to what we did in activity 2, except now it's kind of on steroids a little bit because, there's a lot of extra parts. Okay. And so I will tell you right now that if you try to run a simulation on these parts as is, okay, without suppressing any of the smaller parts, you won't be able to run the simulation because it'll be way too much to mesh and you're going to run into the element limit very, very easily. Okay. And so part of this activity is for you to kind of be the judge of, what's the most important parts. Let me focus on that and suppress kind of everything else. Okay. Okay. Another thing that you'll find useful, and we'll go over this kind of probably beginning of next class, just because I wanted to have today mostly a theory day, is that for the valve, a lot of times you're going to want to apply boundary conditions on the interior of the valve. Okay. And so whether it be like a pressure force or like a some kind of internal force. Okay. And sometimes it can be hard to click on some of those interior surfaces. And so what's useful is this feature called hide faces. Okay. It's not that hard. Basically, you just have to highlight the faces and just right click and click hide. Okay. But we'll kind of, I'll kind of show you how to do that kind of really quickly, probably next time. Okay. All right. So that's the idea of the midterm project. Okay. So you're gonna take one of these geometries, you're gonna run some finite element simulations on it, and then you're gonna write a report. That's basically okay. And so what I have next is kind of the contents of the report, kind of what I expect to see in each section, as well as kind of the deliverables for it. But are there any questions on just the general idea behind the midterm project? Okay. Okay. All right. So let's talk about these specific requirements. Okay. And so the requirements, for your project and for your report, I've kind of broken them down into separate sections. Okay. And so I'm going to go through each of these sections and kind of talk about kind of what I expect from each one. Okay. So let's start with the objective, right? So a finite element objective is not really something we've talked a whole lot about in this class, but it's something that's really important, okay? And so whenever you run any kind of finite element simulation, there is always an objective to that analysis, okay? And so, almost never are you going to run a simulation and not really have any idea in terms of what you're trying to find out. Okay, so you're always running a simulation to basically find out some information, to find some data on your subject. Okay, and so I want you to start thinking about that for this midterm project. Okay, and so I want you to basically look at our two geometries here. Think about how these two geometries or these two kinds of components are used in practice, and kind of almost role play a little bit in terms of if I was an engineer working on this type of system, what would be something that I would like to find out. Okay. And so another way that you can think of this is that it's basically like a hypothesis. Okay. And so, one example of this is, let's take the globe valve, for instance. Okay. And so let's say inside this globe valve here that you have some kind of pressurized fluid running through it. Okay. And so one of your hypotheses could be is that under normal operating conditions, okay, with the fluid exerting, X amount of pressure on my valve, I hypothesize that the valve is going to, not only not break, okay, and so it's going to stay in operation, but it's also going to be within its factors of safety as well. Okay, so that's your hypothesis, and then you're going to run your simulation to kind of test that hypothesis to make sure that it's true. Okay, and so some questions that you can consider when forming your objective is, are you interested in the mechanical stress in a critical area? Okay, are you looking to check for failure? Maybe you're interested in the maximum deflection or maximum deformation. Okay. Maybe you're looking to minimize the cost of production. Maybe you're trying to kind of shave off some material. Okay. Are you working on design? Okay. And if so, what are the design criteria? Okay. But no matter what your objective is, I want you to be kind of very clear about that in your report, and I want you to kind of write about that, in kind of the introduction. Okay. And so, in other words, to kind of boil it down into one sentence, you should know what you're looking for in your finite element analysis, and you should make that very clear in your technical report. Okay. And so, of course, this is a little bit different because normally, you're working on a part or you're working on a finite element in a company, so you kind of know kind of have a little bit more context. Here, I'm kind of giving you a part, and so you have to use your imagination a little bit. I think, you guys are all master students, so I think you guys can all at least picture at least one scenario for each of these parts here where it would be used in practice. And so kind of go off that and kind of build your objective from there. Okay. All right, any questions on the finite element objective? Okay. Next is the finite element methodology part. Okay, so this is where the bulk of the points are going to be. So this is where I'm going to grade you the most on. Okay, and so hopefully what you've gained from the first three activities here is that when you're running a finite element analysis, there are a lot of decisions that you have to make along the way. Okay, so you have to decide, you know, what are the materials that you're using, what are the material properties, what kinds of elements do you want to use, you know, what kind of order are they going to be, how many elements are you going to use? Okay, are you going to add any local refinement? Okay? What are the loads and constraints? How do you apply those loads and constraints? Are they accurate to what your physical situation is? Okay, and so all of these are kind of important decisions that you have to make sure that your FEA is something that's going to be reliable and accurate. Okay. And you know what's important about these decisions is not the fact that you make them, but the fact that you have to justify them. Okay. And so you know a very common problem that you'll find, it's not a problem, it's an important thing, is that when you produce finite element analysis or finite element results, okay, people are always going to be questioning the legitimacy of your FEA. Okay. And so you have to be ready to basically, you know, not only run the simulation, but also be ready to kind of justify and defend kind of how you did it to basically convince people that what you did was correct. Okay. And so we've talked a lot about, you know, meshing, boundary conditions, material properties. And so you guys are equipped with all the information that you need to justify all these decisions. Okay. And so it's important
Dr.
that
Chan,
yes.
apologies for interrupting, but I have a question. Just
Sure.
let me know when you want me to inquire.
Go ahead.
So as you were just talking right now, a question popped up into my head, and that is, what exactly did engineers use before FEA? Was everything by hand, or were they just using codes, or?
Yeah, no, I mean, a lot of it was by hand. So FEA is a fairly recent thing. And so, you know, there was a ton of engineering work that happened before that. Of course, you know, they weren't able to do computations on kind of the exact complex geometry that we're looking at, you know, that we can do in FEA. But they were able to do a lot of approximate models. They were able to do a lot with hand calculations.
Because
So yeah.
you mentioned that a lot of other engineers are going to be questioning FEA. When you say that, are they questioning the FEA method itself, or are they questioning the way you did the FEA?
It's the way that you did the FEA.
Oh, I see.
Yes.
Thank you, sir.
Yeah, because you know there's a lot of ways that you can do FEA, right? And so you know, and you saw it in the last activity, right? And so even just something simple like the element shape, right? So tetrahedrons versus hexahedrons. Okay, we know that there's trade-offs between the two, but at the same time, you know, you can kind of make it work with both, right? And so there's not really a right answer, but it's more in your thought process of, you know, I chose to use tetrahedrons here because of this, okay? And I chose to add mesh refinement because of this, okay? And so that because is really important, just to make sure that, you know, people have faith in your decisions, okay? Because it's very easy to basically take an FEA and produce kind of a very pretty picture with it, but whether that pretty picture is something that's reliable or not, that's a whole other question. Yes.
So in terms of the element shapes, I understand from previous activities, we can get errors.
Mm-hmm.
So how would you justify using it? In terms of using, like when you get errors, it's usually
Yeah. Mm-hmm.
like how would you justify using other element shape in the element size?
Yeah, no, that's a good question. I mean, cost is always a consideration. The limitations of the software is always a consideration too. And so you can say that, you know, because, you know, ideally you would want a much smaller element size because that's going to be a more accurate simulation. But that there's always going to be limits to how much you can do that. Here, you know, in this class, we have kind of a very hard limit because we're not using the commercial version of ANSYS. And so after a certain point, ANSYS will say, okay, no more elements, you know, you have to buy the full software. But in reality, you know, there are limits because, you know, if you run a mesh with, you know, say 40 million elements, that's going to take like literally probably a couple of days to finish the simulation. And a lot of times you just don't have that kind of time because you have deadlines and stuff and you can get the simulations done. So, you know, you're going to have to make some kind of smart sacrifices in terms of, you know, I only have, you know, X amount of budget or I have X amount of time. And so I'm going to concentrate most of my elements here because I know that's where the stress is going to be concentrated the most. Yeah. And so here, you know, you can probably literally say that, you know, I would love to refine the mesh more, but we have limitations with the software. That's okay too. But cost and practicality is definitely a consideration as well. Yeah. Mm-hmm. Yeah. All right, and so most of the grade is going to be based on this part, okay? Because it's not only does it show me that that you can click all the buttons and answers because that's what we're doing the activities, but you're also incorporating a lot of what we're talking about in the lectures in terms of what makes one element type, what situations is it better than another one, or why did you choose to refine in this area, or why did you choose to do the loads in this way, okay? And I've written a little bit more in the report template, which I'll show you in a bit. Okay. Okay. And so this part's important here. And so with regards to the boundary conditions, I want you to do more than just one configuration. Okay. And so I want you to think of at least 3 different scenarios for your part in terms of the boundary conditions. Okay. So you can change up where the fixed support is. You can change up the types of loading. Okay. You can even change the material properties. Okay. And so I want at least 3 different scenarios. Okay. And so, one scenario that you can do maybe is maybe normal operating conditions. Maybe a second scenario would be kind of an emergency. Maybe something hit your part. Okay. You want to see if it can withstand that. And maybe a third condition could be, maybe the same loads and constraints as before, but maybe you change the materials to like a plastic or something like that. And you see how that changes the results. Okay. But I do want to see 3 different scenarios. Okay, so again, you have to use your imagination a little bit, but I think you'll be okay. Okay. And if you're having trouble coming up with different loading scenarios, you can definitely feel free to talk to me, and we can kind of talk it out and kind of see what would kind of make the most sense for your geometry. Okay. Okay. All right, so that's the finite element methodology, and so for the report template, you'll see that I've split it up into material properties, meshing, and boundary conditions. And so, there are, there's more kind of fine-grained organization in this, but that's generally the idea. Okay. So basically every decision that you make in ANSYS, I want you to be able to justify. Okay. Any questions on this?
In terms of like justification, so the 3 different scenarios, like do we do it in terms of, it's like you're showing the mesh, you're showing
so you can use the same mesh for all 3 scenarios. So I wouldn't expect that that's going to be, unless the stress distribution is drastically different between the 3. But you can probably use the same mesh for all 3. But I do want to see like a figure for each loading scenario where like, this is scenario 1. Here are all the loads. Here are the fixed constraints. And so I want to see a figure like that for all 3 scenarios. Yeah.
I do have a question, Dr. Chan.
Oh, sorry. There's one question.
Sounds good.
I'll come back to you, Ivan.
Who's the target audience?
Good question. Yeah. So the question is, who is the target audience? So your target audience would be basically someone of the same, basically someone else in the class. So basically someone with the kind of the same understanding of finite elements. And so you don't have to start from the basics of the basics. You can use terms like mesh and tetrahedron, hexahedrons, and expect your audience to know about that. Yeah. Basically communicating to someone else in the class what you did for this FEA and justifying it to them. Yeah. Go ahead, Ivan.
Thank you, sir. Apologies for interrupting. My question was, when is this document going to be made available? Is it available already?
It is, yes.
Oh,
and so
nice.
I'm going to go through it again. So I'll go through it here. So if you go to the Canvas site, basically everything you need for the project is here already.
Nice.
The document we're going over is the specification. So this is basically the instructions and the requirements. And then I have the template. And so this is a Word doc, so you can just type right into it.
And my follow-up question would be, in the instructions, do you provide where you expect to see the pictures, like include a picture here? Okay.
Yes. Yeah.
So everything is clear and direct.
Yes. Yeah. We'll go over the template after this. Yeah.
Thank you, sir.
Yep. Okay. All right, so once you've justified all your finite element decisions, now it's time to kind of present the results, okay? And so you'll have a section here for the results. And basically for every configuration, and so, we talked about that you have to have 3 configurations. I want to at least see a plot of the total deformation and equivalent stress, okay? So that's at least 2 figures per simulation. But of course, if there are more figures that you want to show, maybe different stress fields, or maybe if you want to zoom in on a particular region, maybe show me one screenshot of your entire geometry and another screenshot of a zoomed in part, that's fine as well, okay? But I at least want a total deformation plot and an equivalent stress plot of your entire geometry. Okay. And this next part's important too. And so, not only do I want the figures in the report, I also want to have some kind of explanation in the text to basically tell your reader, what they should be looking at. Okay. And so this is really important because, I think when you're doing FEA, it's very tempting to just kind of put a screenshot of your results there. And so, you can say the results kind of speak for themselves. Well, if you kind of know what you're looking for and you know what you're doing, like, yeah, the results kind of speak for themselves. But a lot of times, you'll be presenting these types of reports to maybe like your manager or maybe like, the director or something like that may not have kind of intimate knowledge of what you're working with. And so you should still have some text there to explain kind of what they should be looking at. And so, let's say that you're showing a plot of the equivalent stress, okay? And so you can show the plot, and in the text, you can say that, from our simulation, we can say that the maximum stress is X, it occurs here, okay? And the reason it occurs there, it makes a lot of sense, is because we have the loading configuration like this, okay? So you should explain kind of what you should be seeing, and you should explain to the reader, you should explain to the reader, whether your results make sense or not. I mean, they should make sense. And so you should explain to the reader why they make sense, okay? Okay, so that's important. And so, I think the number one mistake that I usually get, it's more for my undergrads, not really for my grad students, is that, they just plop a figure into the text, or they plop a figure into the report, no explanation. And then, I can tell what I'm looking at because, I'm assigning it, but, if it was not me, it would be very hard to kind of tell what's going on. So make sure that you explain your results, okay? There should be kind of, for every screenshot that you put in, there should be kind of a small paragraph that kind of explains kind of what the reader should be looking at and why it makes sense or not. Okay. And just like I said, you can include other screenshots as well, and sometimes that enhances your results. So, at the very least, you should have 2 figures per configuration, and then a small paragraph for each one, kind of explaining what each is. Yeah, question.
Does that also apply to the modeling methodology?
You mean for the screenshots? Yeah. So for the methodologies too, like when you show your mesh and the boundary conditions, you should explain in the text kind of what they're looking at. Yeah. Yeah. Generally, a good rule of thumb is that whenever you're writing a technical report, you should never have we call it like having a figure on an island. And so it should never be kind of by itself. It should kind of work together with the text. And in fact, the figure should kind of enhance kind of what you're saying in the text. That's kind of how it was taught in terms of the stuff. Okay. Okay. And so the last section is conclusion. And so you can have just some concluding remarks. And so this is kind of the part where you relate your results back to your original hypothesis. Okay. And so you can say whether or not your ANSYS results support or not support your original objective or your original hypothesis, okay? You could talk about, if there's any additional work that needs to be done, any additional analyses, and kind of most importantly, because this is a class, what did you learn from doing this project, okay? And so the conclusion doesn't have to be that long. It can be, like half a page. That's usually where I see it in, but, make sure, you write a decent amount. Okay, so that's all the requirements for the project, and so we'll go over that in more detail when we look over the template. But are there any questions just right now? Okay, so the template. So I posted a template onto Canvas. Okay, and so this is basically there to give you kind of a general structure of the report. Okay, as well, it does give you some tips on how to write each section. So please use the template. You don't have to use my font. And so I've had people just tell me to my face that your font is ugly. Okay, so you can change the font if you want. You can change the spacing. I don't really care. But the most important thing is that you've used the same sections. Okay, so I want the report organized in a specific way, just so that it's a lot easier for me to grade. Okay. In terms of the length, I don't really have any requirements on the length. But generally for this report, with all the screenshots that you're including and all the text, usually it's somewhere within the ballpark of usually on the end, closer end of 15 pages. And that's including all the screenshots. And so, I know some people like to go up to 20, 25 pages. And so, I'm not going to penalize you if it's too long or anything like that. But if you want just a rough idea of kind of the average of where most people end up, I'd say the median is about 15 pages. Okay. But if you write more or less than this, as long as you satisfy all the requirements, and you've written about them in sufficient detail, then I'm not going to penalize you. Okay. All right, so I have a rubric as well, and so we'll go over the rubric in a second. Okay. Teams, there are no teams, and so this is purely an individual project, and so everyone has to do their own simulations and write their own report. Okay. But with that said, I know there's only 2 geometries here, so feel free to collaborate with your classmates in terms of debugging issues. Maybe you're having a specific issue with the mesh, and you can ask your friends with that. That's totally okay. But as long as everyone does their own simulations in the end and writes their own report, that's what I care about the most. Okay. All right, and so some final remarks. And so it's going to be a process, and so this is not a project you can do overnight. And so there's a lot that you have to do in terms of just first of all figuring out the simulation, figuring out what you want to do with that, and then writing the report. Of course, is going to be a lengthy endeavor too. So throughout this entire process, don't be afraid. I'm here to help you. So feel free to reach out if you have any questions on the project, and whether it be something simple like how do you want this formatted, or something more complex in terms of hey, I have this issue in ANSYS, and then we can go through that. Okay. All right. Any questions before we jump into the report template? All right, so let's take a look at the report template. So this is the second document that I have here. Okay. And so it's a Microsoft Word document, and so it's you can just kind of type right into it. But if you prefer to use another program, and so I know a lot of people are into using LaTeX nowadays, and so if you want to use LaTeX, feel free to do that. Again, the only thing that I ask is that you use the same kind of section headers, okay, just so it's easier to read. Okay, so first you have your title, you have your author. I've written this part for you, so you were part of the mechanical engineering department here at Cal State Fullerton. This is the address of Cal State Fullerton. Okay. All right, so the first thing you're going to write is the abstract, and so the abstract is a very brief summary of the entire report. Okay, it's different than the introduction, so people get confused between an abstract and an introduction. The abstract is kind of like if you were to summarize your entire report, introduction, methodology, results, in just one small paragraph, that's what the abstract is for. Okay, and it should be very short, so it should be somewhere between 100 and 150 words. Okay. All right, next we have the introduction, and so the introduction should describe any background information, and so this is where you're going to talk about your project objective, okay, and why an FEA is important. Okay. All right, and so a good introduction, what it should do is it should clearly motivate your study. It should describe the objective of your study, and it should describe what you hope to obtain. Okay. You could include a figure as part of your introduction. And so what a lot of people do for this kind of project is that, when you think about, how this part is being used in practice, you can include a screenshot of, this part actually being used in practice. Okay. So you can Google image search something like that. And so the introduction should be fairly short. And so for this report, it should be no longer than a page, figure included. Okay. Okay, then we get into the methodology sections. So we have material properties. And so for this, you should describe and justify the materials that you use for your project. Okay. And so you should use a material that's in typical use. Okay. So don't use like vibranium or anything like that. And so it should be like a real material. Okay. So like things like aluminum, steel, those are pretty typical for these geometries. Okay. Meshing. And so you should describe how you mesh your geometry, describe all the meshing parameters, shape, order, size, and justify all those explanations. Okay. You should show a screenshot of your final mesh. Okay. So I should be able to look at your mesh and kind of judge kind of how good your mesh is or not. Okay. You should also need to talk about the number of elements and the number of nodes in your mesh. Okay. So make sure you specify all of those. Boundary conditions. You should describe kind of the location where they're being applied, as well as the magnitudes and directions for all your loads. Okay. Remember, you're doing multiple configurations, and so you describe all your configurations in this section here. Okay. And when you are talking about your loads, they should be something that's physically feasible, right? And so they should kind of physically make sense. And so you should justify your load by just kind of describing, what real life situation you're trying to model. Okay. Okay. And from there, you have all your results. Okay. So you have your results for the first configuration, the second and third. All of these are mostly the same. So you have your total deformation and equivalent stress, as well as your text explanation. Okay. Then you have your discussion. And so I have some additional discussion questions that you can answer here. And so these kind of relate your results back to your objective. Okay. And here you can talk about, what are some challenges and limitations that you ran into. And then finally, after conclusion, for references, I don't expect you to have many references. You can reference, maybe the course textbook or something like that. But you can omit this section. And so, if you're writing this report, I know you're using the class notes and the lectures. And so, you don't need to credit me. Just, if you do use an outside source, maybe to get some numbers for your loads, maybe you're looking at a technical manual for a valve or something like that, then you can give credit to those things. Okay. And finally, here I have some additional instructions in terms of how I want your tables and figures formatted, just so that they're all consistent between all the reports. Okay. But this report should look nice, and so this should be something that you would feel comfortable kind of turning in your job or something like that. Okay. So not only is it kind of showcasing your FEA knowledge, but it should look pretty presentable too. Because the idea is that when you do FEA, it almost becomes like the way that you show people FEA, it almost kind of becomes like CAD, where you kind of have a portfolio of things. And so what I imagine is that this report is something that you can put into your portfolio as something that you can use to show employers that you know FEA. Not only do you know how to use the software, but you know how to justify all your decisions. And so that's kind of the motivation behind this kind of report. Okay. All right. Any questions on the report template? Okay. All right. So we can go through the rubric really quickly. Last thing. Okay. So here is the rubric. Oh, questions? Yep.
The methodology part.
Yep.
So in terms of the different situations, do we include the respective parts, or do we just include everything that we changed or everything that we're practicing within the votes?
You should describe each boundary condition configuration in that appropriate section. And then if you're going to use two different materials, you should describe those two materials in the material section. Yeah. Yeah. So basically everything should be described in the methodology. The results mostly just show your ANSYS results. So there should be no more explanation of your methodology in the results section. Yeah. Okay. So here's the rubric. And so I think it's pretty straightforward. And so you can see here why I have the template, because each section of the template, I'm grading you on each section. Okay. And so here you can have there's a little bit more explanation here in terms of how I'm grading it. And so you can kind of read that. Okay. And then based on each section, I'm basically, this is like an A, B, C, D, and then these two are Fs. This is F and F minus, I guess. Or the 0, I only give a 0 if it's literally not present. So if you don't include it in the report, that's a 0. But if you at least make an effort, then I give you a 1. But you don't want a 1, you want a 5. Okay, but that's there for your reference. And so basically over spring break, what I'm going to do is I'm going to take, I'm going to make a rubric for everyone in the class. And then, I'm going to mark it according to your report. There are not enough people here today. Okay, and then the last two files that you'll see here in the assignment these are the two CAD files. And so we have the valve and we have the shaft bearings CAD file there. Okay, and so remember, choose one. Don't do both. Choose one for your report, and then focus on that. Okay? And you can change your mind halfway through. And so I'm not requiring you guys to fill out a proposal or anything like that. So if you start with one and you decide you want to do the other one, that's fine. So I believe a lot of people end up changing their mind too. So you're not married to a part. You can choose the other one if you want. Okay. All right. So that's the midterm project. Remember, it's due a month from today, and so it's due on March 27th, the Monday of spring break. Okay. It's going to be a lot of work. And so, it's not something, like I said, I know every professor says this about their work. It's not something you can do overnight. But this one, it's really true because, when you do these parts, I guarantee you everyone runs into some kind of issue in ANSYS. Okay. And it's, you want to start early so that you kind of give yourself the time to kind of debug those issues, because a lot of those issues, they're not just going to go away, right away. And so you want to have time to make sure that you're working through the errors. You're working through, making sure that your mesh is looking nice and pretty. Okay, so make sure you start early, and so you're not rushing it all at the end. Okay. All right. Any final questions before we go back to our regularly scheduled programming? Okay. All right. So that's the project. So that's out there. So everything you need's there. So definitely get started soon. week 6. Okay. All right, so that's the project. And so, like I mentioned before, we're basically done with all of the basics of ANSYS. Okay, so I think kind of we're at a point now where I would say that you can actually apply ANSYS to a lot of practical problems out there. Okay, so starting from today, I would say we're going to cover more, more advanced features in ANSYS. Okay, so stuff that may not apply to every single simulation that you do, but they're common enough that they're good to have in your toolbox. Okay. And so basically from here on out, we're going to be building up our toolbox in terms of, your finite element tools. Okay. And so the first thing that we're going to do is we're going to go back to meshing, and we're going to talk a bit more about that. Okay. And so in particular today, we're going to talk more about the different element types. We're going to talk about the different element types and we're going to talk more about the differences between them in terms of, what you're really choosing when you choose like a triangle over a rectangle or a tetrahedron over a hexahedron. Okay. Okay. So let me start by saying that, you have a lot of options when you're choosing the element types or element shapes. And so far, what we've talked about is kind of purely the geometry of the decision, right? So we know that triangles fit better in some situations when you want to mesh no matter what, okay? Whereas the rectangular elements or the quad or the hexahedrals, those work better, when you have a square geometry with filled space, okay? The differences go a little bit deeper than that. And so, I want to talk about a bit more today. And so, hopefully after today and Wednesday's lecture, you'll have a better idea of, exactly why the rectangular elements are people consider them to be a lot better. Okay. All right. So first, before we do that, we have to talk a little bit about shape functions. Okay. And so we don't really have enough time in this class. It's not really the focus of this class to really go into, what those shape functions are and how they mathematically, factor into finite elements. But even in kind of a, I consider this to be kind of a more of a practical applications type class. It is still useful to understand what the shape functions are and how they factor into the element shape. Okay. And so the shape functions are basically the way that FEA uses to approximate the solution to the underlying equation. Okay? And so the way they work is kind of like this. And so, finite elements is basically just a very fancy way of solving differential equations, right? So that's something we've talked about before. And so normally, if you're taking a math class, you're given an equation you kind of solve that equation from scratch, right? So you make kind of no assumptions and you just solve the equation. And then what you get from the solution is just the solution, okay? The way finite elements works is kind of a little bit opposite to that. So, when finite elements, or when you solve an equation using finite elements, the first thing that you actually do is you assume a form of the solution. Okay. So actually, we did talk about this. And so we talked about this, we talked about element order, okay? And so, when we talk about element order, basically what we discussed was that, that order was the form of that solution, okay? But it goes a little bit deeper than this. And so when you're looking at multiple dimensions, what's considered a linear function and a quadratic function, is a little bit border, okay? So it can either be and so shape functions, that's in essence, that's basically the term that we use for that approximating function, okay? And so what I'm going to do is I'm going to go over, each of the different element types, and so each of the different element shape and order combinations, and we'll talk about, what their shape function essentially looks like, okay? Okay, so let's start with 2D, okay? So let's talk about the quadrilateral elements, a linear quadrilateral element. So a linear quadrilateral element looks something like this. So it has 4 sides, because it's a quadrilateral, and 4 corners, okay? And each corner, we're going to put a node there. So we have 4 nodes in total. Okay. Different node total per element. And so the number of nodes is going to be significant, because basically what we're going to be able to do is that each node in our element is going to give us 1 additional term in our shape function. Okay? So let's see what that looks like. Okay, so let's write out the shape function. Let's write out the shape function for this shape. Okay, so we have 4 nodes, and so that means our shape function is going to have 4 terms. Okay. And so I'm going to use the function t. And so traditionally, T stands for temperature. And so, these notes are kind of adapted a little bit from my other finite element class, 541. And so in that class, we solved primarily the heat equation, because that was the easiest one to solve. So I use t, but that t could be almost anything. Okay. All right, and so this is of course going to be a function of x and y because we're in 2D. Okay, and we're going to have 4 terms here, and so let's start from the simplest term. Okay, and so any polynomial, any polynomial starts with the constant term, so we always start with c0. Okay, then we have each of the linear terms. Okay, so we have c1x, which is going to be the linear term in x. And we have c2y, and so c2y is the linear term in y. Okay. We can have one more term here, right? And so, each node is going to give us another term. Okay. And generally speaking, the more terms that you have in your shape function, the better quality element it's going to be. And so, you're going to be able to capture more rich kind of solution behavior with the more terms that you have. Okay. But we're kind of, running into an issue because, we know that this is a linear element. And so that means our shape function should also be linear. But we're all out of linear terms, right? And so we have the constant term, we have the 2 terms that are linear in x and y. Okay? But we have one more, okay? And so we can kind of spend that extra node on something else. And so the next term up is going to be this cross term actually. So we're going to have c3xy. And so you might be looking at the term, you might be like, wait a minute, that's not a linear term, that's a quadratic term, right? So we have x times y. And so you're right, technically this is not purely linear. And so sometimes what people call this is, they call this a pseudo-linear term. And so even though that's the term itself, is technically quadratic, because if you count the total power of x and y there, it's 2, right? Because you have x times y. But individually, in terms of x and individually in y, it's linear, right? And so we call it pseudo. All right, so that's our shape function, or that's our approximating polynomial for the linear quadrilateral. Okay. So that last term, I think, maybe based on the way I described it, kind of seems like a throwaway, right? But what we'll see is that term actually helps us out quite a lot. And that's the existence of that term and terms like it. And so you'll see kind of the analog terms for the quadratic, as well as the 3D elements. We'll probably do 3D elements on Wednesday. The existence of these terms is part of what makes rectangular elements, generally more preferable than the triangle. All right, any questions on this? All right, and so let's look at its cousin element. And so let's look at the linear triangle. Okay. So the linear triangle has 3 edges and 3 nodes. Okay. And so since we have 3 nodes here, that means our shape function is also going to have 3 terms. So let's write it out. So we have t of x and y is equal to, okay. We start with a constant term as we always do. So we have c0 plus c1x plus c2y. And that's all we can do because we can have just 3 terms, okay? So 1 term per node in the element. Zoom out here. Okay. And so let's look at our two shape functions here and let's compare them to each other. Okay. And so if you look at the shape function for the quadrilateral, which I have up top, you can see that it's exactly the same as the triangular one, except we have that extra pseudo-linear term. Okay. And like I mentioned, that pseudo-linear term is significant. Okay. Because, what the addition of that extra term there, or the addition of any extra term, means that we can capture that kind of behavior in our solution. Okay. And so because of the way finite element works, where we assume a solution first, okay, because we assume a formula of the solution first, we're basically limited to just whatever our assumption is, right? And so, for our linear case, basically what we're assuming is that our deformation or our stress, or in this case, temperature, is that it's going to vary linearly, okay? And so the choice of shape function constricts the type of solution behavior that we can see. So for example, for linear elements, we can only capture we can only capture linear variation of the solution. Okay. And so if our solution varies linearly, that's great. So we can capture it with the linear function. But if our solution varies in some other way in terms of a quadratic, then we're not going to be able to capture that. Okay. And so what you'll see is that as we start to talk about kind of the more advanced elements, what those are essentially going to do is they're going to add more and more terms to our shape functions here to capture more interesting behavior. Okay. All right. Any questions on this? Okay. All right. So let me give you kind of one, I would say, fairly practical example of this, that a lot of people run into. Okay. Let's talk about this phenomenon known as shear locking. Did we talk about shear locking before? I've taught this so many times now that my memory kind of blurs a bit. But basically, shear locking is something that can happen in structural simulations. And so basically the types of simulations that we're doing in this class. Okay? And so what shear locking basically looks like is that it almost looks like the entire geometry kind of just locks up. And so it looks like, you apply your constraints, you apply your loads, but it looks like those loads are barely doing anything. Okay? So the deformations appear very small. And so basically it looks like the geometry is kind of locked up. Okay. All right. So this is obviously bad, right? So we don't want this to happen. Okay. Because this can kind of give you a false sense of security because, you might apply a load and it looks like, hey, the deformations are really small. So it looks like I'm good to go. Okay. But obviously that's not going to be what's happening in reality. Okay? And so this is a phenomenon that occurs specifically for a very specific combination of elements. Okay. It occurs mostly when you use a linear element. In particular, a linear triangular element, so either a linear triangle or a linear tetrahedron. That seems kind of strange, right? So why does it occur specifically for this combination of, order and shape? Okay. If we look at the shape function for the linear triangle, then it starts to make a bit more sense. Okay. Okay, so if we look at our shape function, it looks like this. And let me change the notation here. So instead of dt here, I'm just going to change it to u. Okay. It's purely cosmetic. You can use t, but I'm about to take the derivative of this. So u looks a bit better. Okay. So that was the shape function that we had for a linear triangle, right? So we had 3 nodes, and so we had 3 terms. Okay. And so for a structural simulation, we're going to be using this function here to approximate the deformation. Okay. Okay. And so when we solve the simulation, or we run the simulation, our deformation is going to have that function. Okay. Okay. And so let me take this equation here. Let me take this deformation and let's take its derivative. Okay. And when we take the derivative of deformation in space, right? So we take the derivative with respect to x or y, that's going to give us strain, right? So we have du dx. We have du dy. Okay. These are pretty straightforward to compute because there's x and y only show up once. Okay. And so we take the derivative with respect to x, we get c1. We take the derivative with respect to y, we get c2. Okay. In other words, what you get from this is that for each element or on each element, our strain is going to be constant. Doesn't matter if you take the strain in the x direction or the y direction, it's going to be constant. And this is going to be true in 3D as well. And so in 3D, when we do that on Wednesday, you'll see that, you get constant strain elements. Constant strain means that the stress is going to be constant in the element as well. Okay. And so this is where the issue starts to happen. And so when you start to have constant stress in the elements, then the elements can start to lock up. Okay, because the way kind of the structural equation works is that a lot of times you want to have kind of a very sometimes you have very sharp differences in stress. Okay, and those sharp differences in stress, or I would say rapid changes in stress, that's what causes the deformations to occur. Okay. And so if you have a situation where each element has constant stress, then it's not going to be able to compute deformations in an accurate way. Okay. And so you can see that, if you have a linear triangular element, then you kind of subject yourself to, this kind of behavior. All right. Any questions on that? Question? Oh, just talking to myself. Okay. This issue doesn't occur for rectangular elements. Or I should say it's a lot less common in those elements. Okay. And why is that? Let's look at our shape function again with a linear quadrilateral. And so the hallmark of the linear quadrilateral is we have that kind of extra term there. That's C3xy. Okay. So just like before, I'm going to take the derivative of this. Okay. Switch back to t, but this should be u. Okay. So we take du dx. Well, we get a c1. And so that's the same as the triangle. So that's still there. But because of that pseudo-linear term, we actually get another term as well. We get C3y. Okay. And same thing when we take the strain in the y direction. So we have C2 plus C3x. Okay. And so because we have these terms here now, our strain is no longer constant. We can actually have variations in strain across an element. Okay? Given we can only get the variations in one direction, and it's the cross direction, but that already is kind of a huge difference. Okay? And so for that reason, if you can get kind of rectangular elements, you run much less a risk of doing something like this. Okay. All right. So in general, what you'll see is that if you have a rectangular element and you compare it to a triangular element, the rectangular element is going to have more terms to its shape function than the triangular. Having more terms generally leads to more, I guess you could say, more robust solution properties, more robust solution behavior. And so generally that means it's going to be more accurate. And so you're going to be able to capture more solution behavior, but it also helps guard you against some of the issues that can occur, like shear locking. Okay. All right, so that's kind of another reason to choose a rectangular element over a triangular one, is that its shape function is just more better filled, just because it has more nodes or has more points on its image. Questions? Yes.
Is there a way to detect shear locking when you have more architecture?
Yeah, that's a good question. So the best way to detect that is to refine the mesh. And so shear locking actually goes away. It goes away pretty quickly, but if you refine the mesh a little bit, you can see that the deformations go up by a ton. That means that you're probably shear locking. Because your deformations, it should probably change a little bit as you refine the mesh, but for shear locking, it's pretty drastic. And so you go from like almost no deformation to a lot of deformation. All right, any other questions on this? Okay. All right, so last thing we'll do today, let's talk about the quadratic elements. Quadratic 2D elements, I should say. So let's start with a triangle. I'm going to go ahead and draw a triangle here. The end nodes. Okay. Okay. So we have a triangle. We have our 3 nodes here. Okay. And we want to get a quadratic polynomial. Right now we can't, because we saw that with 3 nodes, the best we can do is a linear function. Right? And so the question is, how do we modify this triangle to give us more nodes? Okay. The answer to that is to just literally add more nodes to the element. Okay. And so what I'm doing here is I'm adding a node in the middle of each of the segments. Okay. We'll call this 4, 5, 6. Okay. And so these nodes here are called mid nodes, because they're literally placed in the middle between each of the original nodes. Okay. So with the addition of the mid nodes, we have 6 nodes in total now. And so that means our shape function can also have 6 terms. Okay. So let's write that out and see what it looks like. And so we're going to start from the bottom again. So we're going to start with our constant term. And we have our 2 linear terms. We have C1x plus C2y. Okay. The next term that we're going to add is our pseudo linear term. So we have C3 xy. And we have the purely quadratic term. So we have C4 x squared and C5 y squared. Okay. And so you can see here that we're now venturing into the quadratic territory. Okay. So we have terms that are purely quadratic here, and what allowed that was the addition of the extra nodes. Okay. All right. Any questions on this? All right, so let's do the next one, which is the quadrilateral. And so just like before, we have our 4 corner nodes. I'm going to add 4 more mid nodes. So it looks just like that. Okay, and so with the addition of the 4 mid nodes, that means we have 8 nodes in total. And so that means we're going to have 4 terms in our shape function. Okay. All right, so our shape function looks like this. So Txy, C0 plus C1x plus C2y plus C3xy plus C4x squared plus C5y squared. Okay. So that's the first 6 terms. We need 2 more. And so we have C6 xy squared and C7 x squared y. So once again, we have terms that, strictly, technically speaking, are not quadratic, but they're pseudo quadratic. All right, so the last 2 terms, technically, they're power 3, and so they're not, quadratic, but they're individually in x and y, they are quadratic. Okay, any questions on this? And so, of course, the same trends that we talked about for the linear case apply here as well. Okay? And so the more terms that you have, the more accurate and more robust your simulation is going to be. But of course, all of that comes at a price. Okay, so I believe we talked about this before. So quadratic elements generally are more expensive, or they require more memory and more computations than linear elements. And so what you'll see is that, if you produce a mesh on a geometry, okay, and you keep the mesh size the same, but when you switch from linear to quadratic, the number of elements, it might change a little bit, but it's going to be mostly the same. But what's going to be different is the number of nodes. So you're going to have a lot more nodes doing quadratic elements than. Okay. And so this is, again, something that you have control over. And so you can choose whether you want to do linear or quadratic. Okay. In my personal opinion, generally, I would prefer to use quadratic elements just because they are a lot more robust. And ANSYS actually makes it really easy. It's literally just a flip of the switch, whether you do linear or quadratic. Okay? That's not necessarily the case in a lot of other softwares. So because of how easy ANSYS makes it, I would say most times, with the exception of some cases where you can't really use quadratic elements like dynamics, we'll talk about that in Activity 5. Most of the time, quadratic is going to be preferable because it's more robust. Okay? And the cost difference is usually not that extreme. It's something that you would notice. Okay. Okay. And so before we go, I'll leave you kind of with one thought. Okay? And so we've already seen that, just by going from a 3-sided shape in a triangle to a 4-sided shape in a rectangle, we get a ton of benefits, right? And so, by using a rectangle, our shape functions here are much more better filled. Okay. And so, a question that I've always had for the longest time is, why stop at 4, right? So why don't we go to like a pentagon? Why don't we go to like a hexagon, right? So those should be even better, right? Because we have more nodes and more sides. And so that's going to be even better for our shape function. Right? Well, in theory, yes, but then, you kind of run into the issue where, you've already seen for a rectangular element for hexahedrons, sometimes it's really hard, if not impossible, to fill a space with hexahedrons. Right? Once you start getting beyond that, it gets to be almost impossible unless you have a very constrained, very kind of simple problem to do a mesh with like a pentagon, like a hexagon. Okay, it's just not practical. So for most finite element softwares, they stop at these rectangular elements. That's because no one has really figured out how to do a pentagon mesh or hexagon mesh. I will say though that if you do go out there and discover that, you'll probably make a ton of money because there's ANSYS probably pay you a lot of money for that algorithm for sure. But there's also a good reason why no one's coming up with it. All right, any final questions before we wrap it up for today? Most likely not, because you have because when you take the derivative, you end up with a lot of terms that still have variations of x and y, and so you never get a situation where you have constant stress. That's the main thing that causes shear bonding. All right, any other questions? Okay, sure. All right, not related to the lecture, but for the homework assignment, can you quickly show how we can change the dimensions for part 5? Oh, yes. Yeah, so for when you're changing the dimensions in activity 3, you have to do that back in design model. So you have to close ANSYS Mechanical and then modify the geometry in design model. So it's a separate program for it. Yeah. So if you look back to activity 1, design model was kind of the first program that we opened. That's the one where you can actually set the dimensions of different parts. Yeah. So basically, you change the dimension, you kind of remake the geometry, and then you open up mechanical again, and then you remesh and do all that stuff. In design modeler for our yes. Well, you shouldn't have to make the remake the geometry, but if you open up that geometry in design modeler, you should be able to modify it. Yeah, I can show you really quick. Maybe that's kind of the last thing. But are there any other questions? Okay, all right. So let me go ahead and verify that that the dimensioning is still working. But if not, thank you guys for coming today. It's really cold, it's really wet out there, so make sure you guys are staying wet or dry and warm. And I will see you guys all on Wednesday.
Thank you, Dr. Chan.
Yep. Okay, so let's go ahead and import geometry. Okay. And so, this geometry is made in design modeler. So, I'm not going to set up the FEA, but to modify the geometry, you basically right click this and edit the geometry in design modeler. And then here you can change the dimensions. And so for the sign post, we want to look at this one. Okay. And so it's a little bit hard to see, but the sketch is kind of down here. Okay. And so to change the dimensions, you would go down in this bottom left and change it this way. So the base diameter of the post is 1.12, and then you would change that up or down depending on what you want to do. Oh yeah, so remember there's two CAD softwares in ANSYS. So there's Space Claim and Design Modeler. So you want to make sure you do Design Modeler. Yeah. Yeah, we'll use Space Claim on the next activity, so you'll see it then. But for now, you want to use Design Modeler. Yep. Mm-hmm. Yep. Have a good night. Okay. All right. So I'm going to go stop the call. Let me stop the recording.